Thank you, WPDCL for the invitation, and thank you very much for the patience that you guys are showing. I know it's a lunchtime. I'll not take much long. I'll try to finish it fast. Uh, everyone is going gaga about lithium-ion battery, and we all know that lithium-ion battery has its own flaws, and there is nothing like. And a number of speakers has told today that there is nothing like a single solution for all the applications. So what we actually need is we need to look beyond lithium-ion battery, the way we are doing for the fuels right now. And this particular presentation is going to be about that only. So before going ahead with the presentation, I want to focus on this. Say that if we will expand our horizons of what fuels are, then we will find that metal can actually suffice all the needs as far as the electricity is concerned. And we all know about the market for quite some time now. What we don't know, and maybe very few people know, that there are certain other metals, that is sodium, aluminium, zinc, which can also do the same thing which lithium and lead are doing, with least complications that lithium brings in. So So if you see here, these are certain parameters which these particular metals they possess. If you can see that aluminium has a specific capacity, it's second to lithium, which translates into better energy density. And when we talk about sodium, it has a pretty good standard electrode potential and can give a very good power. The best thing about these three metals is that we can get in-house. As far as we know that similar to what is happening with the fuels nowadays, that we are highly dependent on OPEC countries. In future, the same thing will happen with lithium, that 90% of 90% of lithium it comes from China, Australia, Congo. Ultimately what will happen is, apart from OPEC, we will be depending on these countries. Hence we need something that can be sourced in house, or these are recyclable. Therefore sodium, aluminium and zinc are certain kind of metals which can do these kind of job for us. So before moving ahead, I just wanted to discuss the technological trend, but it will give us that where these particular batteries are at this particular moment. So these particular divisions that has been made, it's based on the number of patents that are coming in and the adoption that is happening on these batteries at an industrial level. So you can see that all these three batteries that we'll be talking about are at the pre-development state. They are emerging. At sodium ion, you can see that I have given a dashed mark here because its similarity with the lithium ion battery, its adoption is little bit faster as compared to other two battery tech. Lithium ion and lead acid, we know that they are already into the market, and lead acid is pretty much very saturated or stabilized tech, wherein we have a complete control over our forward and backward supply chain. Now starting with the techs, so first is aluminum air battery. So this particular technology, it is pretty old. It started in 1962. It's kind of a primary battery. It's not a rechargeable battery, or you can say that it is a mechanically rechargeable battery. It has a very good theoretical capacity, around 2.98 ampere hour per gram. Has a very high theoretical energy density, which is almost 3 to 4 times higher than a lithium ion battery. Aluminium, as we know, it's being used everywhere, and it's inexpensive, abundant, and quite environmentally friendly, unlike lithium ion battery. The main component of these batteries are aluminum anode, a porous air cathode, and an electrolyte solution. How this particular battery works? So you have aluminum at the anode, which actually acts as a fuel. So once it comes into contact with the KOH electrolyte, it starts burning. To enable this particular burning, you have an air cathode, at which the oxygen starts reducing, and hence a complete cycle takes place. The standard electrode potential of this particular battery is 2.71 volt, which can give you a pretty good power as well. This is a aluminum air cell design. So you can see over here. So this is actually a running type, or a flow type battery, wherein you have an electrolyte inlet here. Electrolyte enters from here. Then you have an aluminum cassette, which acts as a fuel, as I mentioned earlier. And on both the sides, you have air cathodes from where oxygen enters into the electrolyte. So first electrolyte enters into the cell, and then these are the exit points for the electrolyte. Then you have caps and notches for the electrical connections and everything. So you can see here the major components which makes this particular battery. So you have an air cathode. So your air cathode is divided into three parts. One is which is in direct contact with the electrolyte, which is known as the catalyst layer. Then you have a current collector, which is made up of nickel, steel, or copper coated nickel. Then you have a backing layer from where oxygen actually enters into the system. Then we have anode, which is made up of aluminium electrolyte, which can be any alkaline, either KOH or NaOH. Because we are using KOH, and KOH has a tendency to react with CO2, so hence we need a scrubber as well, so that only fresh oxygen enters into the solution, into the cell. As far as balance of plants is concerned, so these are the equipments. We can call it as an ancillary equipments. They do not take part into the reaction, or they are not the active component, but they enable cell to work. So you have a pump, you have a tank wherein the electrolyte is kept. Pump is used for the continuous flow of our electrolyte, and pipeline and an air blower for the continuous oxygen flow into the cell. As far as aluminum economy is concerned, it's pretty simple. As soon as you have, so once the aluminum is burned out in an aluminum air cell, you will have an aluminate. These aluminate can directly be sent to the aluminum smelters. So we have a number of smelters available in India. You can directly send it to them. They can convert these aluminum plates, aluminates into aluminum plates, and then you can again reuse it. So it's a there is nothing that has to be incorporated, as we have in lithium ion batteries. So pretty simple. As far as the use cases of this particular battery is concerned, number of startups they are coming in. One of them is an Indian startup, Log9 Materials. They are working on this particular technology, and they have started a number of POCs with this particular battery. So as you can see here, the use cases are mentioned here. So it can be used in a standalone, it can be used in a marine application, it can be used for a 3 and 4 wheeler, as well as in heavy duty vehicles. The second battery technology that we'll be discussing is the zinc air battery. So again, this is also an oldest technology that has been that has been there in the market for quite a long time. And if you I don't know, but if you guys know that a lot of people, they wear hearing aids. So these kind of batteries actually goes into those kind of hearing aids because of their very high volumetric energy density. This particular battery tech has a very low fabrication cost, because we are using inexpensive zinc. Again, similar to aluminum air battery, it also consists of a zinc anode, a porous air cathode, and an alkaline aqueous electrolyte. Working of this particular battery is also similar to aluminum air battery, wherein zinc anode burns into a zincate, and on the cathode side, oxygen burns into an hydroxyl ion to give you a complete cell reaction. But this is a rechargeable battery. So herein you can convert this particular zincate into a zinc again inside the, in a cell. So there is no mechanical recharging happening here. It's a simple electrical recharging that will happen. These are the major components. So you have again, similar to the aluminum air battery, you have an air cathode divided into three parts. Then you additionally you have a dimensionally stable anode here. What it does is it enables the recharging of our zincate. So usually during recharging, the oxidation reaction that happens on an air cathode, so it makes it it decreases the durability of our air cathode. Hence, to do that, a separate anode is being kept so that it can enhance the life of our zinc air battery. Apart from that, all other equipments are pretty similar for the zinc air battery as well. Its economy is also pretty simple. Similar to aluminum air battery, whatever the zincate is getting generated, it can directly be sent for the zinc electrowinning, wherein electrochemically zincates can be converted into zinc. Even though it is a rechargeable battery, once it will reach to its end of its life, you can simply send the zinc for its recycling, and those then once recycled, these zinc can be reused again. Here I have shown a simple design which an American company Zincate is nowadays using. So this is a flow type zinc air battery, wherein in you know a zinc air flow. So this is your energy generation unit, and this is the electrolyzer unit wherein your zincate converts into zinc. So this all happens in a, it's an online kind of thing. So all happens in a single battery system. So whenever the energy is required from the system, zinc air battery will start giving the energy, and whatever the zincates are getting generated, they can be sent back to the zinc electrolyzer, wherein once you will start incorporating electricity, these zincates can convert it into zinc and then can be sent back again to for the for a battery usage. Use cases. So this zinc air battery is, actually it's nowadays is getting a lot of traction because its usability in a large stationary, as far as the stationary is concerned. So Zincate is using this particular technology for the grid stability. Zincate and Finergy, again they are using it for a standalone in our tower applications. Then it has found some application in marine as well. And as I mentioned earlier, that they are being used as for button cells in a hearing aid devices. The third and the last tech is sodium ion battery. So I hope everyone is aware of lithium ion battery. So you can call it as a cousin of lithium ion battery. The inception of this particular battery happened along with the lithium ion battery, but because of certain superiority of lithium ion battery, lot of efforts had been downgraded, as development efforts were not too much as far as the sodium ion is concerned. Sodium ion, even though not as good as lithium ion battery, but it has a pretty good energy density. The best part about this sodium ion battery is that it is 1,000 times more abundant than lithium. Hence, it makes it pretty much accessible, and a lot of geopolitical tensions can be reduced if you start using sodium ion battery. As far as the composition is concerned, it also consists of carbon anode, as similar to lithium ion battery, and sodium enriched cathode, and an electrolyte which is non-aqueous, similar to lithium ion battery. So this is a typical reaction that happens. So instead of lithium, you have a sodium metal oxide here as a cathode, and as far as the anode is concerned, you have a carbon, wherein during a reaction, during charging, sodium ion starts intercalating into the carbon lattice, and during discharging, they starts getting back to the cathode. So there are different kind of sodium ion variants are available, as there are variants of lithium ion battery based on the cathode. So there are different variants of sodium ion battery as well based on the cathode. So one is where Prussian blue is being used. So this particular cathode has shown to have a very good specific capacity, and hence we can match at least the LFP variant of lithium ion battery with this. Then you have a layered oxide, which has a capacity of somewhere around 200 milliampere per gram, and then we have a polyanion, which has a little bit lower, but it has a very good power density, hence it can be used for another applications which are power intensive. As far as the battery type is concerned, so you have a cylindrical cell. I think all of us know what cylindrical cell is. The problem with the cylindrical cell is that it has a very poor thermal management. To improve the thermal management, a lot of companies are now moving towards the prismatic cell, which due to their flat structure, thermal management becomes quite easy with them. There are certain other variants which is known as pouch cell. Even though there are not much standards available with it, but certain tests have shown that thermal management can be very good, and we can achieve a very good volumetric as well as gravimetric capacity with the pouch cells. As far as the key component is concerned, the cathode, as I have mentioned, that you can use a different cathode. The anode, the current collector is aluminum sheet here. Anode is again a hard carbon, so we are not using a soft carbon as we are using it in lithium ion battery. The current collector is again aluminum sheet. Electrolyte is NaPF6, which is a sodium version of LiPF6. We are using a separator and a aluminum based casing here. As far as the sodium economy is concerned, similar to lithium ion economy, not much is available. As you all know that as far as the lithium ion battery is concerned, only 5% of its component can be recycled. The good part about sodium ion is that at least sodium can be recycled. If you think about Prussian blue cathode, which is an organic organic material, so you can easily take out sodium from it. Hence it's the recyclability of this particular battery is easier as compared to lithium ion battery. So definitely it can have an edge over lithium ion battery in that case. So again, the use cases. So I would like to mention here that this particular battery, because understand that lithium is very small, whereas when you see that sodium is pretty big, hence it does not carry much energy. So it's not an energy intensive material. Therefore, it cannot find the use cases where energy intensive applications, as for example mobility. So you need a very high energy density as far as a battery is concerned. So sodium ion battery cannot be used there. But because of the usage of hard carbon and the mobility of sodium ion, the aluminum. So aluminum current collector that we are using here, we can achieve a very high power in sodium ion batteries. Hence it can be used in a power intensive applications. And so you can see over here the use cases that can be derived from sodium ion battery. For comparison, this is a graph that we have drawn. So you can see this is a gravimetric energy density and a volumetric energy density. Based on these two requirements, how different applications can be divided. So you know that as far as the grid electricity storage is concerned, energy density is not much of a factor here. You need a very high volumetric energy density because so that the footprint can be lower. So for this particular application, sodium ion battery can do justice to it. Then lithium ion battery, definitely it's a good option there, and zinc air is also a pretty good option. As far as the high energy density applications are concerned, which is in electronic devices or planes and drones, so there high energy density aluminum air battery can fit in perfectly. Okay, as far as electronic devices and EVs are concerned, other lithium ion variants can go in there, but aluminum air battery cannot go there. These are certain other comparative differences between the three technologies. So as I have mentioned, so as far as the refueling is concerned, aluminum battery it's it's a mechanical, whereas zinc air battery can be mechanical as well as electrical, and sodium ion battery is all electrical. Cycle life, so as far as zinc air battery and aluminum air battery is concerned, the cycle life, it depends completely on the air cathode that is there. So it's if you have a good air cathode, you will have a very good cycle life. Whereas for sodium ion battery, it can go up to 3000 to 4000 cycles, which is pretty good as far as the lithium ion battery counterparts are concerned. Balance of plant, as I have mentioned, for aluminum air and zinc air battery, you need a lot of balance of plant. Hence, the volumetric capacity of there is pretty low. Comparatively lower in sodium ion battery, but again similar to lithium ion battery, you need an active BMS in this particular case as well, which is the fourth point. Now during an operation, so when we talk about energy efficiency, so when we talk about a balance of plant, so you need a certain amount of energy to run those balance of plant as well. So this is where so that is that whatever the energy that this particular battery is generating, so that is getting consumed for its own operation. Hence when we talk about the power requirement during operation, so for the running of pump and blower, aluminum air and zinc air battery, they do need a BMS, so hence it's not much. Concern for aluminum air and zinc air battery, the heating component is their cathode, and for sodium ion battery, cathode availability of cathode material, it's quite challenging, because at this particular point in time, no one is working rigorously for the development of cathode, and hence in future it might start getting a little bit easier. As far as recycling is concerned, aluminum and zinc recycling is already there. They they are doing it. Sodium ion